We're going to start the class then. Today, we're going to start by discussing artificial intelligence, its definition, and some of the preconception and misconceptions that people have about AI. And then we'll try and come up with a workable, pragmatic definition of what we mean when we talk about AI, sort of looking at the areas that where they overlap and what is common between them. So if you have followed the, let me switch. If you have followed the media in recent years, then undoubtedly you will have heard about artificial intelligence. A lot of articles have been written about it. This is the great age of AI. New applications became possible. Great successes for AI were proclaimed by the media. But the question is, what do we actually mean when, or what do people mean when they talk about AI? So let's start thinking about that. So if you had to come up with a definition of artificial intelligence, then what is it? What applications today are AI? Do you interact with an AI system in 2021? When? How? If you think back about the stories in the media, a lot of them were written about artificial intelligence and breakthroughs in artificial intelligence. But what exactly did these programs do? So let's talk first about the AI applications. So one that was very much publicized was, for example, the DeepMind Go playing program. Right? See if I can get a link to this. And that was actually 2017, not 2016. It looks. I think I have the brackets wrong. No. Ah. I just check that. I forgot how to do links properly. Okay. So one of them was DeepMind. Anything else? Well, when people talk about autonomous driving cars, that was earlier, I guess, starting in about 2012 up to today. That's considered an AI system. Before Go, of course, people were playing chess. Deep Blue beat the Kasparov, the human world champion in chess, in 1996. So here the role of AI in autonomous cars. You can find lots of papers about that. Other applications that you interact with every day. There's actually very many of them with respect to speech recognition. That's considered an AI problem. So when you talk to the bank and they ask you to say your phone number or whether you want to open or close an account, any kind of customer service, automated customer service, it's an AI program. On the internet, some of the applications of AI that have attracted attention because of their potential harm would be bots and disinformation campaigns. So a lot of Russian bots were involved in the US election, something like that, trying to veer the public's opinion about certain topics. They are becoming more and more important. The Facebook, Apple, Amazon, Netflix, and Google companies sort of what would you call it, algorithms for banning or questionable content. Those are all AI systems or considered to be AI systems. If you apply for a loan or a credit card, those are done by machine learning systems nowadays that decide whether you are a good candidate for a loan, where it's likely that you repay the money, not run off with the money. That's done by machine learning systems nowadays. And another application that I think is actually quite questionable and quite socially sensitive and dangerous is recidivism. Recidivism. So I will post a link to it to the American Bar Association. Autonomous cars and AI. So companies like Tesla are now considered AI companies. And rightfully so. Bullet list. Right. So let's talk about recidivism. That's my personal view, fairly sensitive topic, and it sort of shows the pervasiveness of AI algorithms and the importance of ethics in AI. So what happens with this particular system is that if you commit a crime and are caught and then brought to the judge and then sentenced, so let's say somebody stole an iPhone or something, and he gets caught by the police, then he has to go in front of the judge, and then the judge has to find them guilty. Then they will be sentenced, right, to jail usually. So the length of the prison sentence depends on the expected chance of recidivism, which means chance of committing another crime after you are released from jail or prison. Right? So if this was your first theft, then the judge will maybe think that this was that you made a bad choice, but are not necessarily a bad person, so they will give you a lighter sentence, less time in jail. If this is your 50th theft, then the judge will think that, he will just get out of jail and then commit another crime, and then he will be in front of me again, so you will get a longer sentence. Now, that requires a judgment call by the judge, and increasingly states in the US, the prison systems use AI programs to estimate your chance of recidivism. So now, when it used to be the judge that would look at your case and then make a decision estimating how likely it is that you are a career criminal as opposed to somebody that made a temporary error. And that increasingly is now done by programs, by AI systems. And that, of course, can be quite has a huge impact on people's lives. And the problem is that the AI systems are completely opaque. So if you know anything about deep learning networks or neural networks in general, the kind of technique that people currently use, they cannot be understood. The rules that they follow cannot be understood by humans. They are simply millions and millions of floating point numbers, activations through the network. So if the AI system says that, a very high chance that you will commit another crime, so you have to go to jail for 6 years instead of 1 year, then nobody really knows why the AI made that particular decision. If it's a judge, at least you could ask them, I guess, why they made a certain decision. But with an AI system, nobody knows what they were, what they based the decision on. And in recent times, we have lots of evidence of systems, AI systems, being what's called biased towards race, gender, things that are actually protected that by law we're not allowed to discriminate against. And even if not by law, it doesn't, as a society, we value the idea that everybody is created equally. We want to give everybody an equal chance. So to put in the The most common cases in the US would be that black people are disadvantaged and are sent to longer prison terms than white people for the same crime or similar crime, simply because the AI system determined that, and simply because the AI system only sort of spit out what it was trained on, and we don't really have any control or knowledge about the trained system, the training data that is used. So there have been lots of cases of bias in AI. The most famous one is, let's see, no, this one. And by the way, that's another area of AI where you interact when your computer unlocks, because it looks at the camera and it sees your face. That is also an AI system. But of course, this face recognition is actually So black people are misclassified, misidentified much more often than white faces. So um, that has shown up in Zoom meetings where using a virtual background, their faces will be blurred out. In Twitter, portrait images that are dealt with AI. Now, if your Twitter picture is not quite right, then that is sort of a minor inconvenience and you can fix it yourself. If the system sends you to jail for an extra 5 years, then that's a much bigger problem, right? So not all of them are not all AI algorithms and biases are equally harmful. And of course, China is now the world leader in sort of face recognition and policing. They have gone and installed thousands of millions of cameras to watch and penalize people for infractions automatically, like jaywalking and things like that. But we don't really know if one group of citizens is going to be targeted or harmed or selected, misidentified more often than others because these systems are biased, but they are inherently opaque. We cannot really tell how well the system works and what kind of people it discriminates against. So obviously, as a society, we don't want that to happen. We think it's wrong to target people based on the color of their skin. And now we have these AI systems that are rolling in, and we don't really know what they use in order to make their decision. Whether they would illegally, if a human were to do it, that would be illegal. So if an AI system does it, then all of a sudden it's okay. Then I think that would also be wrong. So from a social point of view, I think the rapid rise in AI technology has definitely led to a situation where we're now left the genie out of the box, but we don't really know what the long-term impacts of that is going to be. So interesting times ahead for everybody. But now more not considering the ethical aspects of the technology. What exactly makes these applications special? What makes them AI applications? What do they have in common? And in fact, on first sort of view or looking at it superficially, not that much, right? We talk about credit scores, we talk about face recognition. We talk about driving a car. Other applications are in more applications in computer vision. So vision is sort of definitely an important aspect of it. You can see, but not all of them. So the legal recidivism score, for example, is not based on vision at all. So what exactly makes these applications AI? What do researchers investigate when they do AI research? And that's still done today, of course, but now we can also do some real-world applications. But initially, a lot of AI research was focused on solving puzzles. Because we didn't have the compute power to do things in the real world. And planning and problem solving were important areas of AI for AI research. So the idea is here all the different kinds of puzzles. Logic puzzles, chess puzzles, huge array of those. Planning and problem solving, logistics. Which I guess is another AI application that we should mount up there. And I actually forgot to say that, but almost every one of you uses the Google Maps or Garmin Navigator kind of applications to find your way to some unknown location. That's also an example of an AI system. And a very successful one. So combined with GPS now, the computer can tell you take the next road, turn right, and then you will reach the movie theater. Problem solving, logistics, so navigation. And those are also areas of AI. And let's have a look at, because we were talking about the not being able to understand the system, the opaqueness of the decision making done by the AI. Sometimes it has fairly funny consequences. I found that particular video here last year, and you may have seen it, but they are quite a lot of the AI systems, I believe, are overhyped at the moment. Certainly the autonomous driving capabilities are not such that we could have millions of self-driving cars on the road right now. And also face recognition systems that work quite well, most cases, still have really bad errors that occur. So I just want to download this video. So let's just give it another minute, 45 seconds. So early AI researchers focused on puzzles and various games like Blocks World, Dr. Eureka, Tic-Tac-Toe, chess, mainly because humans that can solve these kind of puzzles are considered to be intelligent. They're manageable to do in size wise, like the problem was not too big. And they are fun to do. Lots of people enjoy doing these puzzles, so to try and do them with the computer was a good first step. But these kind of puzzles and games are actually quite a unique style of problem. And nowadays, none of the games really, the computers, the AI systems can beat the best human players in all of these kind of puzzles and games. So the Go was the last one to fall, like I said, 2017, but chess already 1996. Nowadays, nobody talks about humans playing against computers in chess because over the last 30 years, or over the last 25 years, computers have just been getting better and better at playing chess. So now humans really have no hope of beating a computer in chess anymore. But we have, let me structure this. And I mentioned this already previous times. It's called Moravec's paradox. The exact formulation by Moravec was the observation that contrary to what you believe, the things that you think require a lot of AI, require a lot of intelligence, like reasoning, actually requires comparatively little computation compared to actually the sensory skills that are required in order to manipulate and live in the physical world. So Moravec said that in one of the seminal papers, he said that it's comparatively easy to make a chess playing program, but when it comes to perception and mobility, we don't have anything that is matches the performance of a 1-year-old child. And I think I mentioned it already. Yes, we can have the best AI company systems can beat the human world champion in Go now, but any one of my students can write a computer chess playing program that can beat 80% of the people in the world playing chess or Go, simply because most people are very bad at playing chess and playing Go. These kind of problems are not very amendable, not very easy for human intelligence. So here, let's have a look at that video because it just demonstrates that in a fun way. So how many? So ImageNet is a database of 14 million images that have been classified by humans. And now, in about 2 years ago, the claim was that, the big news was that some deep learning, some AI systems can classify these images better than humans. So that means that you get the impression that AI systems now are very, very good at recognizing images. But in fact, when we have lots of cases where the classification task of the AI system is like this. So I'm not sure if you saw that video before, but the Scottish Football Club is broadcasting their soccer matches, but they don't want to spend the money on a cameraman, so they used an automatic camera system that tracks the ball. So basically they don't need to pay somebody to look for interesting shots of the soccer game. They only have the automatic system. The automatic system always follows the ball, and that should be a trivial task, right? If I give a picture of a soccer match to a little child and ask it where the ball is, then it will get that right all the time. But last Saturday this happened. So here they're playing, right? So the AI system has to track the ball. Now if I show this picture to anybody, any human, even little kids, ask them where the ball is, then they know this is where the ball is, right? And then we can run the game some more. And where's the ball? Now the ball is there. Very easy task for a human. But now the spectators got upset because the referee was bald. So the camera system was tracking this guy's head as the ball. It thought this is where the ball is. So the people couldn't enjoy the soccer match because the ball is over here somewhere. Nobody knows what's going on, but the AI system was tracking the referee. He keeps going, get back to this guy. Shoop. So, what's going on there, you may ask, because... Wait. then it goes longer. Yeah. So it just keeps showing how it goes back to this guy. So this is a pretty funny mistake of an AI system. Fairly benevolent. I mean, very benign. No big harm done. But of course, could if the system would have misclassified this as somebody with a gun, then things could have been much more dangerous. So the question then is, how is this possible though? I mean, we have these claims that a deep learning system can now perform better than humans, and then it makes a mistake like misclassifying somebody's head as the ball. The reason for that is because of the error that the way that we count errors or misclassifications in ImageNet. So ImageNet has, I don't know how many, like 10 different types of dogs. And there are some dogs that are quite similar, like a German Shepherd and a Rottweiler, for example. Those are pretty close. So sometimes humans misclassify German Shepherd for a Doberman dog. So this is counted as -1 for the human, right? This is counted as an error. But no human, it doesn't, so it's just an error. No human would say, if you show him a picture of a dog, they would never think that this is a horse, for example, or a washing machine. But the AI system, if it has a picture of a dog and then it says washing machine, then that's also counted as -1. And of course, classifying thousands of images is sort of a tedious task. So sometimes people just make I'm sure sometimes people make mistakes just by having to do a lot of these classifications or not paying attention, something like that. So it's easy to get these kind of small mistakes into the classification. They're counted just as bad or strongly as completely wrong classifications, like a dog and a washing machine, which no human would ever do, or the head and a ball. That kind of misclassification would never happen for a human. So you have to pay attention to exactly what the researchers and the people were measuring when they talk about the performance of humans versus computers. Often it's not an apples to apples comparison. Often it's an apple to orange comparison. So it's not nearly as meaningful as you may think it is. Of course, researchers are continuing to improve the algorithms and coming up with better methods, and the AI systems are going to improve. But at the moment, their state, the performance of these systems is based more on wishful thinking than actual performance in the real world. Similar task and application is actually the misclassification. If you try and implement voice recognition over many sentences, it is actually quite difficult to it's quite difficult to get the right voice recognition, especially in a noisy room or noisy environment or a poor microphone. So with our robots, we would like our robot magicians to be able to react to the audience. That is still a difficult, very difficult problem where even simple things like yes and no, the human user has to say that multiple times. If you run it on the device itself, using cloud-based recognition works a lot better. And that's also one of the current state of the art. One thing that has actually impressed me that has been getting a lot better without much fanfare in recent years is text-to-speech synchronization. That actually works quite well, or at least to me it does. Let's say daily news, USA, sure. Oh, there's nothing. Okay, let's take something not controversial. America's favorite foods. Because the other stories were all about crime and war. So don't want to depress people too much. So if I go to translate google.com, then let me translate this into German because I know German. So this translation into German is actually very good. So the language models have improved dramatically in recent years. That's also GPT-2, GPT-3 can do amazing things. I can also translate it into Chinese. So that's, I don't know how good that Chinese translation is. You can try it out yourself. What I think is even more impressive is the speech recognition. So
it's important to do breakfast right, and that's pretty easy with the number of American favorites so good that they can honestly be enjoyed any time of day. Every American is familiar with a stack of pancakes or bacon and eggs paired with a slice of butter.
So this is pretty nice text-to-speech capability. Like it's reading pretty well. We can try.
Es ist wichtig, richtig zu frühstücken. Und das ist ziemlich einfach, da die Anzahl der amerikanischen Favoriten so gut ist.
And this is not actually the best one that I heard, but it sounds quite nice. Given to about 5 years ago, the voice is a lot less robotic. Of course, you can still tell it's not a human speaking, but that's mainly because it doesn't include things like these kind of intonations or ams. So the text-to-speech on, let me see if I can log into Tolino. Oh wait, I didn't switch my camera, right? So you couldn't actually see it, but so here
It's important to do breakfast right, and that's pretty easy with the number of American favorites so good that they can honestly be enjoyed any time of day. Every American is familiar with a stack of pancakes or bacon and eggs paired with a slice of buttered toast, but there's a lot more to be found in various regions of the country.
yeah. Oh, and I cannot access this. Oh. Okay, and here the German translation is also very good. Like it's basically flawless. Where speech recognition, I think, is lacking behind. It's not doing such a good job. So where's the... And of course, one fun thing you can do is, let's try translation several languages. So let's go English to Chinese to German to Spanish to English, and then compare what we actually get. So we start with the English text, then I said we translate it into Chinese. Okay. Then I take this text, translate it into German. This is still the same, so I won't be fooled that easily. Then I can translate it into Spanish. And I only use the common languages because I think the fewer people the language speak, the harder it will be for the system to do the translation. and then from Spanish back into English. And it's almost the same. So it did a good job translating throughout these different languages. So that means the Chinese must have been, and the Spanish must have been pretty reasonable too, in a sense, because otherwise it wouldn't have been able to recover. If there would have been major mistakes in any of the translations, then this chain eventually would have had to be broken. And I think in this case, they didn't actually have any errors in the translation, or there were no differences between the input and the output, which is very impressive indeed over these multiple languages. So now let's have a look at puzzles and sort of see if we can get to the underlying features of problems that we use AI in order to solve them, where we use AI in order to solve them. So for puzzles, I like to play the Professor Layton games. I don't know if how many of you actually know them, but they're a lot of fun, and they're basically adventure games, but they're just collections of puzzles. So you may know these kind of games, and this is the one with the top hat is Professor Layton, and he solves these mysteries, but they are basically just one puzzle after another. And now there's a new one with his daughter. And they're a lot of fun to play. The puzzles are interesting. The plot is not so important. And they're all fairly highly rated games. Like people like them 85%, 84%. So let's have a look at a typical Professor Layton game puzzle. Of course, they are also in newspapers and lots of other sources for puzzles where you can get them from. But Professor Layton has sort of some fun puzzles. So I will pick a couple of them, and then we can try and work out for one of them how you would actually implement it and try and solve it on a computer. And that will then allow us to understand better what these AI systems actually have in common and what makes something an AI system. So here's a very common puzzle. It's a very famous one. I'm sure there's a Taiwanese version of it. It's been around for, people have been doing puzzles for thousands of years. So some of them are culturally very dispersed and have been around the world in one form or another. So the wolves and chicks puzzle is a very famous one. Here's the picture of it. And the instruction is that get the 3 wolves and 3 chicks seen below to the other side of the river while obeying the following conditions. No more than 2 animals can ride the raft at the same time. There must be at least 1 animal on the raft in order for it to move. If more wolves than chicks stay on either side of the river, the wolves will eat the chicks and you'll have to start over. You can move the raft as many times as you like, but this feat can be accomplished in as few as 11 moves. And then the UK version has slightly different wording. So here, that's the puzzle. You have 3 small chicken, 3 chicks, and 3 wolves. And you have a raft, and then 1 or 2 animals can go from the left side to the right side, and then can get on and off the raft, and you have to move all the wolves and all the chickens over to the right side. The farmer has to move usually there's a farmer that moves the raft rather than the wolves and the chickens. And the problem is that if there's more wolves on one side of the river, they will eat all the chickens, in which case the farmer would have failed to move his wolves and chickens. I believe the puzzle is originally from Russia, but there's different versions of these kind of river puzzles too. So now think about how you would solve that puzzle as a human. Or try and find the solution, try and solve the puzzle yourself and see how you would do that. But don't look up the solution, because that's not a lot of fun. So move all the wolves from the left to the right side, maximum 2 animals on a raft. At least 1 for the raft to move, and the number of chicks must be greater than or equal to the number of wolves at all times on a side, on both sides. So looking at that puzzle then it's sort of clear you can or give it some more time. How do you solve this kind of puzzle? Well, first thing is that we use abstraction, right? A lot of detail is ignored or left out. So we know that it's not important because we weren't given that information. So things like the weight of the raft, the length of the river, the color of the chickens, also all those are low-level details that we don't care about in this particular puzzle. They are not specified. Some of the things that are specified are not specified. Others are sort of given in the figure, but would be the color of the chicks, the size of the wolves, and some other information. So now looking at that puzzle, you can sort of think about what you can do. So you can start playing around. Unfortunately, there's no online version that you can experiment with. Actually, there may be. Well, otherwise I would have written one. Yeah. So you can start playing around. So you can do things like move put one wolf on the raft, move it across. Then you have one wolf here on the right side. Or you can put two wolves onto the raft, move them to the right side. Or you can put one chicken on the raft, move it to the right side. And then you realize that that's illegal, right? That will not work, because then if one chicken is gone on the right side, that means there's three on the left, three wolves and two chickens, so that would be illegal. And similarly, you cannot move two chickens onto the raft to the right side, because then there's three wolves and one chicken on the left side, and that would be illegal. So as you play around with it, most people, or for me when I tried to solve this particular puzzle, you'll realize that then other things. So after you play around for a while, for example, you may realize that it doesn't make sense to put one animal onto, in this case, it doesn't make sense to put one wolf onto the raft and bring it to the right-hand side. And we cannot move any of the chickens only, right? Because if I move one wolf, then I can move the wolf over to the right side, but then I cannot do anything, because there must be at least one animal on the raft. So if I want the raft to go back to the left-hand side, then the wolf has to come back. And in that case, I just wasted two moves, right? Because I'm in exactly the same state that I was in before. I was in exactly the same picture that I was in before. So nothing has changed. I have three on the left, three wolves, three chickens, and the raft is on the left-hand side. So that was a wasted effort. It was definitely a detour. If that does lead to a solution, if I do find the solution, I can solve the puzzle in two fewer moves by just not doing that. So after you think about this for a while, then you can sort of realize that what you want to do, what you could do, would be two wolves over to the right-hand side, or one wolf, one chicken. And those are the only two things that you can do that sort of makes sense, right? None of the other approaches would allow you to make any progress towards a solution. So first we would realize that from the start, but now instead of calling it start, I'll just call it initial. Just to give it a fancy name. And the first thing that I sort of realized, like we mentioned, is that because of the abstraction, the movement of the raft is a crucial part of this. So whenever I move the raft left to right, then something interesting happens. At other times, I cannot possibly make any progress towards a solution. So from the initial state, we cannot move 1 or 2 chicks because then wolves eat the chicks on the left side. Then after some more thinking, we can sort of figure out that it doesn't make sense to move one wolf from left to right because he would have to move because in the next step the wolf would have to come back with the raft, and then the situation is repeated, right? Situation is the same as what we had before. So now, just to be a little bit more formal, when we're actually moving the raft, then we are, of course, physically executing an action because we're moving the raft. More importantly, as far as the puzzle is concerned, we're sort of moving into a new situation. The puzzle changes. So we call that actions or operators. And before, the important information that we have about this puzzle, the crucial information, that is where the animals are. Which animals are on the right side and which ones are on the left side. And we call that a state of the puzzle or a state of the world. And this start is called the initial state then. So I've not given a mathematical formulation for what we mean by state and actions and operators, but it's sort of intuitively clear. It's sort of one position of the puzzle that we're trying to solve, one current set of facts about the puzzle in a more abstract sense. In the wolves and chicks problem, the state would be where the animals are, and then I can, with the raft, move animals from the left side of the river to the right side of the river, or from the right side to the left side. Then that's very naturally maps to state of the world and actions and operators. But sometimes we're working in abstract spaces and it's not so intuitive, it's not so clear how to visualize and represent what we mean by the state of the world or what the actions and operators are. One nice thing about puzzles is that usually the states and the actions are fairly easily defined and understood intuitively. If you found out that you ended up in a situation where you moved one or two chicks and that's illegal, so now it's impossible to solve a puzzle, you made an illegal move, then you have to go back in when you're trying how you solve the puzzle. That's called backtracking. In artificial intelligence research, the situation being the same as before, that also has a special name that's called a state loop. And we'll see why that is a problem in AI systems later on. So it looks like we have two choices. That we can try at the initial state. First one would be move one wolf and one chick to the right. Or I can move two wolves to the right. So then the question is, which one do you want to pick? And unless you already solved the puzzle, or unless you have solved these kind of puzzles before, that's not easy question to answer. You wouldn't really know at that point, if this is your only exposure to the river crossing puzzles, you wouldn't really know which one would be better, right? Option 1 or 2. Move one wolf, one chick, or move two wolves. And then So at this point, we have to guess. Okay? Try out a couple of things. So now when we have to guess, then we want to do this on a computer, so we have to come up with a reasonable procedure, an algorithm, a strictly defined procedure that helps us do that. And we basically need to do some bookkeeping now. Particular what ideas we tried already. What options we still have available. And then this would be the sort of first attempt at a computer solution. Algorithm to solve that puzzle. So that bookkeeping is called basically a search procedure, because now I have to take a guess. I don't know whether I don't know the solution, so I don't know if moving two wolves or one chick, one wolf is better. So I sort of need to try things and then see what happens. So we try one action, let's say move two wolves, and then see what happens. Because now when I move the two wolves, I have to remember that this is not the only thing I could have done. I could have also moved one wolf, one chick. And now I move the two wolves, and then the procedure sort of repeats itself, except now I have two wolves on the right-hand side. So I can bring two wolves back. That doesn't make sense, right? Because then I end up in a state loop. I'm again at the same state that I started out with. that doesn't seem to make a lot of sense. In this case, it definitely doesn't make sense. So I don't want to do that. So then the next thing I can do is, the only thing I can do is move one wolf back, right? So when I move one wolf back, then I can I can go back with one wolf, one chick, or I can go back with two wolves, and then all the wolves would be on the right hand side, all the chickens on the left hand side. So then I can continue from there. So the procedure sort of repeats itself. We're in a loop. But it's also clear if that fails, let's say I end up where I cannot do anything except go into a loop or go into an illegal state, then I have to go back to a previous choice that I had. I have to backtrack, right? And so this procedure is called a search algorithm then, or a search procedure, because we're trying to find a solution by basically guessing or guessing and trying to hope that we find the correct solution by luck. And of course, later on in AI, we'll look at not using luck, but some more elaborate version of luck. But this idea that we have to try things out is an important one in AI. In a sense, it's at the crux of AI. So, what did I want to add here now? That resulting state, when we apply an action and then see what happens, that's called the current state. And so this runs in a loop repeatedly. So, okay. Now when you think about that, if I keep track of all the choices that I have, then I make a choice, then I get new choices because I move to a new state. If I can keep track of all of those choices, then I will eventually end up either finding a solution, or I will find out that I did something wrong and it's impossible to find a solution now. Then eventually I can go back and backtrack to try the other approaches. Now, yes, that's what I wanted to add here. What do we actually mean by a solution? By a solution, we mean that we have a sequence of legal steps that move us from the initial state to the goal state, where the goal state would be the wolves and the chicks all over on the right-hand side of the river. The initial state, all the wolves and the chicks are on the left side of the river. So this just defined some of the terminology that we use in artificial intelligence research to talk about special properties of the problem. So we have the goal state. We use search. We have the concept of a current state, which is sort of the simulated world that we're in right now, what the current state is. So let's think about this search algorithm and see why, if you read this, why is AI even difficult, or why do we think that AI is difficult? And not just me, lots of other people think it's difficult, right? If it's like this puzzle with our initial state, our actions and operators, if I have those defined, then I can apply all the possible actions that I have. And then I can see where that leads me to. Then I can recursively apply operators to the new current state. And eventually I'll find a solution, or I will find out that I made a mistake, in which case I have to go back, I have to backtrack. Then that seems to me, or that seems to be a fairly straightforward algorithm to implement, right? And in particular, for this kind of problem, it is actually quite easy. And you can easily write a computer program that sort of follows that approach and finds a solution to the chicks and wolves problem. So to get a better understanding of why this is difficult, let's see how many let's look at how many possible operators actions I have per state. So the state in this case would be First of all, I need to know which animals are on the left side of the river, what wolves and chicks are on the left side of the river, and which ones are on the right side of the river. I also need to know the position of the raft, because I need to know whether I can move the raft to the left or to the right side. So how many possible actions operators do I have for each state? Is a question that is important in this context. Now, to find out the exact number, you can, first of all, that number is not going to be the same for each state, right? Because like I said, if I have 3 wolves, or if I have 1 chicken on the left-hand side and or 1 wolf on the left-hand side and 2 wolves, 3 chicken on the right-hand side, then from the raft is on the right-hand side, then I could move 1 wolf or 2 wolves, or 1 wolf, 1 chicken, or 2 chickens. Those are the choices that I would have. If the raft is on the left-hand side, then the only choice I have is to move the 1 chicken. So the number of actions that I can execute varies based on the state. So now for the sort of reasoning, for the thinking about AI, it doesn't really matter that this number varies. We just use the maximum number of those. As you'll see later on in the analysis, it doesn't really make a big difference in the further analysis. So to simplify it, we calculate the maximum number of actions that we can execute on any state. So what is that maximum number of actions? Send your answer in the following question prompt. So what is the maximum number of actions that I can execute for any state in the wolves chicks puzzle? So not just from the initial state, we basically, with a little bit of reasoning, we came up with 2. However, the loop won't actually occur. I won't actually notice that until the another 2 steps. So I need to simulate another step. So that's not really counted then. So for the initial state, I guess there would be 3. There would be 1 wolf, 2 wolves, or 1 wolf, 1 chicken. So for the initial state, where 3 wolves on the left, 3 wolves on the right, the answer would be 3. But what is it for any state? What will be the maximum for any state? Moving each chick wolf is counted individually. Or that's a good question. Does it mean each wolf chick is counted individually? Yes. However, it's also clear that wolf 1 and wolf 2, moving wolf 1 and wolf 2 is the same as moving wolf 2 and wolf 3. So the wolves don't have names. It doesn't matter which wolf I bring across. It's just the total number of wolves. So actually it wouldn't be 3, it would be 4. If we don't, because I can think about, no. Yeah, 3. Because moving the chick would be illegal. So think about that. What's the maximum number of things that we can do from any state? only for I'm not sure what you mean by left to right and right to left, where they're different. After we move, yes, that's correct. For the state after moving one wolf plus one chick to left, that is correct. But it doesn't make sense to multiply the numbers there. I think it would be adding them together. So the way to solve that problem, first, the raft, right? You can either have one animal or two animals on the raft, right? If you have one animal, then you have two choices. You have one wolf or one chicken on the raft. If you have two animals, then you can have two wolves, you can have two chickens, or you can have one wolf and one chicken. And those are the only possibilities that you have, right? For any state, doesn't matter which one, you definitely have less than 5 actions. 5 would be the upper bound, right? Because if I can either move one or two animals. If I move one animal, then it has to be one wolf or one chicken. And I don't care which chicken it is, as long as it's on the right-hand side. So whether it's Chicken Tom or Bob or Jill, that doesn't matter. For the two animal cases, I can have two wolves, two chickens, one wolf, and one chicken. And that's the same as one chicken and one wolf. Doesn't matter where the wolf is sitting on the raft, if it's the first animal in the raft or the second animal on the raft. That doesn't make any difference. So the maximum number of actions is 5. One wolf, one chicken, two wolves, two chickens, one wolf plus one chicken. Now, this number 5 is called the maximum branching factor. So now, the other important feature that we need to know is the number of solution steps, or the length of the solution. Now, for this puzzle, It's 11 steps. So we have the current state, we apply an operator, we get a new current state, or have to backtrack. If we don't have any legal actions anymore. So you can sort of think of this space as a graph where the states are the nodes and actions are the links, the edges between nodes. Let me just check quickly. Okay. Tests. So let's actually draw this graph. At least the first part of it. And 0, 1, 2, 3, 4. And I'm gonna specify 3 wolves, 3 chicks, and the raft on the right side of the river. 1, 2, 3, 4, and nothing on the left side of the river, nothing on the right side of the river. So then things that I can move 1 wolf. That will give me 2 wolves, 3 chicks, gives me the raft, and 1 wolf over on the other side of the river. Or I can try and move 3 wolves, 1 chick. I can move 1 chick to the right hand side, but then that would be an illegal state, because then I have 2 chicks and 3 wolves on the left side, which would be illegal. So is there a diagram now that I can use? Okay, I just draw it for the first one. So 3 wolves, 2 chicks, duck, duck, duck. The raft, 1 chick, and that's illegal. And 2, and 3, and 4. So then I can move 2 things. So I can move 1 wolf, 1 chick. Or I can move 2 wolves, or I can move 2 chicks, but that's also illegal. Zero, 1, 02, 03, 04, 05. So this will be the first step of the puzzle, right? We have 3 wolves, 3 chicken on the left side of the river, then 2 wolves, 3 chicken, 1 wolf over on this side, that's legal. 3 wolf, 2 chicken, 1 chicken over on the right hand side, that's an illegal state. Then we have 2 wolves, 2 chicken. On the right hand side we have 1 wolf, 1 chicken. 1 wolf, 3 chicken. Right hand side 2 wolves, or 3 wolves, 1 chicken, so that's illegal if we move the 2 chicken to the right hand side. So then we can now pick the next states. So let's see the ones that follow from here. So now I have 1 wolf on the right hand side. Then the only thing I can do is bring that wolf back, right? So I end up with 3 wolves, 3 chickens, and a raft. And that now is a loop. So node 1, I cannot really do anything. Then node 2. From node 2, that's an illegal one, so I don't want to do that. Node 3. Two wolves, 2 chickens, right side. So I can go 3 wolves, 2 chickens. The raft over on the right hand side. That will be illegal. One 6 is an edge I want to draw, and here I have 3 7. Two wolf, 2 chicken, 1 wolf, 1 chicken. So 3 wolf, 2 chickens. That's illegal. Or I can go to state 8. 3 wolves, 2 chickens, 3 chickens, and have 1 wolf over here, and that's legal. Then we have 4. Now I have 2 wolves, so then the only other thing I can do is nine and 10. Bring them both back. That would result in a loop, which is not good. Or I can bring 1 wolf back. That will be 10. So we have 4, 9 and 4, 10. A. 4A. So now our graph grows, right? As we keep expanding more and more possibilities. So then now we also see that moving the 1 wolf over to the right hand side doesn't make any sense, because next state we're forced to do a loop, and there's no way to bring that back into a solution then, or we can just stop because I end up in exactly the same state here. 3W, 3CR, 3W, 3CR is exactly the same state. Here also we end up with the loop if we bring those 2 wolves back. So that cannot lead to a solution here. This one is immediately illegal. This one is illegal. So now we're sort of have possibilities open. Still 3, right? This one can lead to a solution. So bringing the 2 wolves and then 1 wolf back, that is still possible to lead to a solution. This one is wrong. 2 wolves, 2 chicken. Right, 1 wolf, 1 chicken. So that should be, I bring back 1 chicken. So that should be 2 wolves. One chicken, that brings back 2 wolves here, not 3 wolves. Okay, yeah. 2 wolves, 3 chicken, or 3 wolves, 2 chickens. That will be legal. Then let's do one more step. So we still have 3 wolves, 3 chickens, 3 wolves, 2 wolves, 3 chickens on the right, and 1 wolf on the right hand side. Now that's basically the same as this state. Right? So I end up with the same state. Let me just rerun it. I end up here or here. And those are actually both the same state, right? 2 wolves, 3 chicken on the raft on the right, and 1 wolf on the left. Left and right rivers. And those are the only 2 possibilities that I still have that are sort of can be expanded. But so node A and node 8 is exactly the same, so we will move this one from 4 to 8. So now you can see we both end up in the same state, which is why this is a graph. So as you can see, the search space is definitely a graph because it has multiple paths between 2 nodes of the search space. In particular, in this case, 3W 3CR to 2W 3CR 1W. There's 2 possible ways through that space. So we're dealing with a graph here. However, it's much harder than trees. So for analytical results, we assume that each path is different, which makes this not a graph, but a tree. Only one path from root to each node. This is the theoretical reason for doing that. There's also good practical reasons, but I will explain those in the coming class. So that means we actually change the graph and now I have to do the A here again. No, 2W, 3 chicks, the raft, 1 wolf. And now we call this one 4A. So here's our graph now, our tree now. So now this one and this one, we just assume that they're two different nodes, but in fact they are the same ones, but we just ignore that that fact. So then let's build the next graph. So possible successors that we have are 1 wolf on the right hand side, so 8, 8, 2 wolf, 3 chicken, 1 wolf. So now what can move over to the other side? I can go through 1 wolf, 3 chicken, 2 wolves. But that is a loop because I already had that on my path. So I can move 1 wolf over, I can move 1 chicken over, which will give me 1 wolf, 2 wolves, 2 chicken, 1 wolf, 1 chicken. That seems to be legal. I can move 2 things over. So I can move 2 wolves over. That means no wolves. Three chickens, 3 wolves. I can move 2 chickens, so 1 chicken left, to 1 wolf, 2 chickens, and the raft. Oh, I have to move the raft. Right, the raft is now on the right hand side again. 2 wolf, 1 chicken, raft, 1 wolf, 2 chickens. And that's illegal. Or I can move 1 wolf, 1 chicken, so that would be 1 wolf, 2 chickens. The raft over on the right hand side. And now I have 2 wolves, 1 chicken, which is also illegal. And that's the same for the other node. So this would be node 8. So we have 8C, 8D, 8E, and 8F. And that's the same for node A. E, F, G, H, I, J, K, A, G, A, H, A, I, A, J, and eight K, and here I'm missing 1, 8B. So here's our next graphic then, where we expanded the current state, which will be here, this state, 8, this state, and this state. And now we have new successors, 2 wolf, 1 wolf, 1 chicken, 3 wolves, 1 wolf, 2 chicken. So we have 2 possibilities there, and we have another 2 possibilities here. And I can continue doing that. So one thing you can see is that actually this would be a lot of work for up to 11. Right now I've done 1, 2, 3 applications of the operators. So one thing is clear, it's that if we follow this procedure, then we're guaranteed to find a solution, right? Definitely I can continue doing that. I won't find the solution, but we can see it would be a lot of work because so far I've only done level 3 and it's a lot of bookkeeping that I need to keep track of, and it won't be a lot of fun. It would be very tedious to do that. So let's try and estimate how many nodes I have to draw if I do try and draw the graph until level 11, until solution. Well, then we can sort of see it depends on how many successes I have for each node, what I call the branching factor, and how many levels deep I have to go. Because if I assume that every node has 5 possibilities and I assume I'm dealing with a tree, then at the first level I will have 5 nodes. At the next level I will have 5 nodes. Each one of those has 5 successors, so 25 nodes. And at the next level I would have 5 times 5 times 5, 120 nodes. So level 1, five nodes. Level 2, level 3, level 4, 5 times 5 nodes. And then there, 5 times 5. Each one of those has 5 children. So here we have 5. That's equal to 25. That's equal to 120. That's equal to 5 to the power of 4. 625 nodes. In general, for level K, we have 5 to the power of K nodes. So for 11, to find the solution then, we have this many nodes roughly, or we estimate this many nodes that we need to expand. That would be 148 million nodes. Okay, so that's the end of the morning class for today. We'll do some more programming exercises in the evening, starting at 6 o'clock, and also some more analysis and sort of general analysis of AI prompts, trying to come up with a workable definition. You can think until the afternoon, you can think about what all these problems have in common. What is the binding property of all of these problems? And then I will see you at the next class today at 6 p.m. Oh, and I forgot slides. AI, definition of AI. And here's the link to the Google Colaboratory for this class today, this morning. So bye-bye, and I'll see you in the evening.